Good morning, everyone. My name is Ryan, and I'm from UC Berkeley, as Ken said, and I'm excited to share what we've been working on. So when we think about robot learning and the capabilities that we want robots to have, we want them to be able to prepare food for us. We want them to be able to dexterously manipulate objects. We want them to fulfill our orders, maybe drive us from place to place. And we want them to be able to do this all in unstructured environments, to generalize to all kinds of things, right? But where we are today, of course, is that when we deploy them in the real world, they don't always work, right? Might even be safe to say that robot learning doesn't work yet. That's why we still work on it, because we want it to work. We want it to be robust enough for things like industry solutions, where you need to deliver something like 99% reliability, or you can't have a feasible business. So is this something that is in the distant future? Well, not necessarily. There are all these companies today that kind of fix this with a certain solution, and that is to have a human in the loop, right? So if you have a human in the loop, you can catch those edge cases that robots can't handle, and then that hybrid system of human plus robot can actually get you that 99% reliability. And it might be that only a few robots need help, or maybe only a few new robots need help at any given time. Then one human can monitor multiple robots at the same time. So, overview of today's talk, I want to give a little bit of background on interactive imitation learning, then go over this algorithm that we're proposing, give a brief overview of our results, and then a look at what's next. So, imitation learning is the idea that a robot should be able to learn from human feedback and examples. And it's one of the dominant paradigms of robot learning today. There's these 4 great choral papers you'll hear about at this very conference that either learn a reward function or learn a policy from humans. And it's been able to do a diverse range of complex robotic tasks. In its simplest form, and the most popular form, there's behavior cloning. So here, the human is providing a set of task demonstrations, and these are provided in the form of observations, and there's corresponding action labels. And the robot minimizes some kind of loss function that encourages its actions to be similar to those of the human, just via something like supervised learning. Now, does this work? Not always. If you're paying attention to Byron Boot's tutorial the other day, what you can encounter is something called covariate shift, right? Or distribution shift, where due to compounding error, the robot eventually reaches a state that the human has never seen before, and now it has no idea what to do because it doesn't have any reference behavior to imitate. And what this results in is something called an imitation gap between the performance of the robot policy and the performance of the human policy. And the way to fix this is with, of course, online human feedback. What that means is human labels on the states that the robot actually visited, because this will teach you these little recovery behaviors that will get you back to that region where you actually know what you're doing. And the state-of-the-art algorithm for doing this, as most of us know, is Dagger, or dataset aggregation, where the idea is that the human is going to provide an action label for every single state that the robot has visited, and over time, it'll just iteratively do that and close this gap. But Dagger imposes a really high burden on the supervisor. You have to label every single state that the robot has visited, which motivates other techniques for doing this. So that's where interactive IL comes in, or interactive imitation learning, which is this new, not new, but recently gaining interest paradigm where the human or the robot cedes control to a human, and the control switches over between the robot and the human. And the nice thing about interactive IL is that it can be used flexibly at training time when the robot's still learning, or it can use at execution time when the robot and human are working together to improve the reliability of the policy, kind of like those companies are doing. Or you can combine these both, use that data that you got from that human, use it to fine tune the policy, but also care about reliability. And this can be in something like a continual learning framework. So the central question here is, how do we switch control between the supervisor and the human? And the reason this is tricky is because, okay, say you're all the way to one extreme, and the human is just teleoperating the robot all the time. Well, then you have probably great task performance because he's a human expert, but really high burden on the supervisor, right? It's not scalable at all. You have to be controlling the robot at all times and only one robot. On the other end of the spectrum, maybe the robot's in control the entire time. Now there's no burden on the supervisor, that's great, but your performance probably isn't doing so hot because of that imitation gap and other issues. So is there a way that we can balance these competing objectives, right? Good policy performance, but also less burden on the human supervisor. So one approach that people use for doing this is human-gated interactive imitation learning. And the idea is kind of what it sounds like. The human is the one that is deciding when do I take control, when do I give back control. But in order to do that, you just have to continuously monitor the system, right? You have to, even when you're not in control, you have to see like, okay, this is when I have to step in. So when you scale this up to a large number of robots per human, or maybe a long period of time, now this isn't so feasible after all. So another way to do this is robot-gated interactive IL. That's the counterpart to this, where the system itself is the one that decides when should it ask for help, when should it give back control. Of course, this is trickier because the system isn't an expert human, so it uses all kinds of heuristics like maybe action discrepancy or uncertainty and things like that, and then threshold on these values to determine when should I ask for help. But many prior robot algorithms or robot-gated algorithms fail to strike this balance between supervisor burden and policy performance. They result in a lot of context switching between robot and human control and other kinds of undesirable phenomena. So to this end, we introduce this new algorithm that we call ThriftyDAgger, which provides new intervention criteria to hopefully better strike this balance. So let's ask ourselves this question. When should a robot ask for help? So I want you to think about these two quantities. On the x-axis here, we have novelty. And novelty is just, have you seen this data before, right? If you're in a place that you've never seen before, you probably don't know what you're doing, right? That's being off the training distribution. So that's the axis. So then let's talk about risk. So risk isn't a super common term, but in this case, we're saying, what's the probability that you fail the task, right? Then you would say that's risky. If you have a high probability of failing whatever task you're doing, that's risky. So in this case, let's say you're doing an autonomous driving situation, and your risk is crashing the car. Okay. So if you're on a highway on a sunny day, not novel, not risky. You've seen this plenty of times. You know exactly what you're doing. It's all is good. But if you're in a snowy environment, say you don't have a lot of snow in your data, now you don't know what you're doing, right? You probably veer off to the right, maybe you crash into the tree. This is novel and this is risky. Now, our key insight is that a lot of prior work would like correlate these two things, and they are highly correlated, but they're not the same thing, right? There are these off-diagonal terms. So there can be states that are novel but not risky, right? Say like a wide open dirt road. Maybe you've never seen it before, but you're not going to crash. Like you can go in any direction here. Or it can be risky but not novel. So maybe you have seen a human demonstrate how to drive a tight cliff, but it's really hard to do that without falling off the cliff, right? You have a very narrow region of allowable motion. So maybe in that case, you would rather cede control to the human than take your chances driving this cliff. So how do we actually do this novelty estimation? So we train an ensemble of deep neural networks, and each of these neural networks is bootstrapped on a subset of the training data. And intuitively, if you have a state that's not very well represented, that is novel, compared to your training data set, these different networks are going to disagree what that correct action should be, more than if each of them has seen something like that before. So we threshold on that variance to kind of give us an estimate of that novelty. And the other component, risk, we propose this novel risk metric, which is a Q function. So assume that our task can be specified by convergence to some goal set, then we can say, estimate the discounted probability of reaching this goal set. And in this case, that would be estimate the discounted probability of succeeding at our task. Then risk would be 1 minus that, or the probability of failing at the task. And in order to approximate Q, we train this sample-based function approximator Q hat by minimizing this mean squared error Bellman loss, which is pretty much the standard objective, but we switch that reward term to 1G of S, where 1 is an indicator for whether or not you're in the goal set. Now, another thing you have to pay attention to is how do you threshold on these novelty and risk values to determine, when do I switch to human control, when do I switch to robot control? A lot of prior work leaves these as parameters to tune, but they can be unintuitive. Like, what do these numbers mean? And performance can be sensitive to that. And it's almost its own form of supervisor burden. You don't want to run your algorithm multiple times just to figure out, what these parameters should be. So instead, what we do is we let the user provide an alpha, and this alpha is your desired intervention rate, or the ratio of number of interventions to number of robot actions. So say I know I'm only going to be available 1% of the time. I'll set alpha equals 1%. And then using this, we can use our historical risk or novelty values to kind of take the inverse CDF of that and find the 1 minus alpha quantile and then set those thresholds accordingly. So putting it all together here, we're going to, if we're in autonomous mode, we're going to switch to supervisor mode if our novelty is sufficiently high or our risk is sufficiently high using those automatically computed thresholds. And the nice thing about this decomposition is that we only depend on this risk term when the policy or when the state is not novel. Because if it's novel, it would have already switched, which means that it's a familiar state, which in turn means that we can probably trust that Q function that we trained because it's in the familiar region. In the other direction, if you're in supervisor mode, we check if our action discrepancy is sufficiently low, which turns out to be a more tightly correlated with novelty, because when we're in supervisor mode, we do have both robot and human action, and we check that the risk is sufficiently low. Right. So now let's move on to some results. So first, we evaluate on this peg insertion task from a RoboSuite developed by our friends at Stanford and UT Austin, where this ring is initialized in some random pose. You have to grab it, move it over to a target location, and then thread it through this peg at the end. And the reason it's hard is it's very long horizon. This is like 100 or more time steps. So by the time you get to the peg, it's often the case that you're not exactly in the right position, and it becomes this bottleneck to task progress. So what we find is that compared to ablations, compared to baselines, with fewer interventions, ThriftyDAgger can get a higher autonomous success rate, which hints to the fact that, okay, we're better able to balance this task performance objective with this human supervisor burden objective. However, here it does ask for more human actions on average, and this is because of this conservative risk criterion, which kind of doesn't give back control unless it's sure that the robot can complete the task on its own. We also evaluate our algorithms at execution time. So remember here, the goal is to optimize the policy of the hybrid robot plus human, and they're working together to do this task. Again, we see a similar thing where fewer interventions plus higher success rate, and in this case, we're matching the success rate of the Oracle human ThriftyDAgger, where an expert human is constantly monitoring the task and is deciding when to intervene, when to not intervene. And notice that the number of actions is a lot lower now and actually comparable to the baselines because this risk critic is less conservative once the policy is better, right? Now it's not going to fail as much, it's not going to be as worried about you doing the task. We also do some physical experiments. So here is a surgical robot in our lab doing this cable routing task where we're, from images, we are routing this cable in a figure-8 pattern around several of these obstacles. So what happens here? Well, a similar thing happens. So our algorithm is comparable to ThriftyDAgger, which is an oracle in this case, since the human is deciding these intervention points in terms of the success rate. And it's actually, this task is too hard for behavior cloning. It's prone to distribution shift. And we request a comparable amount of interventions and actions to that oracle, despite the robot being the one to request those actions. And again, the number of actions falls significantly at execution time, and here is only a small fraction of the total episode, 1.5 versus 61.3 robot actions. And this last thing I want to talk about is this cool thing that we did, this user study, where here we were interested in the question of, okay, maybe this is a scalable algorithm. How do we apply this to control of a small fleet of robots where there's one human, multiple robots? So we recruited 10 human subjects, and each controlled a fleet of 3 robots in simulation performing that same peg insertion task from earlier. And we compared these 4 algorithms. 3 of them are robot-gated, 1 of them is human-gated, ThriftyDAgger. In the robot-gated algorithms, what we did was we said, okay, whenever a robot asks for help, you have to help it. And if multiple ask for help, they're going to queue up after each other. But if no robot is asking for help, then what you'll do is make progress on this independent game you're playing, the game you're playing called like memory or concentration, where you have a set of face-down pairs, and every time you turn them around, you can kind of get an idea of what they are, and they only get cleared when you get pairs. So you can imagine if you're switching a lot between these 2 guys, your performance on this memory game is going to suffer. In the human-gated version, we say, okay, forget about the memory game. Your job right now is to control all 3 robots at the same time. You get a little bird's eye view on the left, and just make sure that all these guys can complete them as much as possible. And what we found is that our algorithm requested fewer interventions, fewer human actions, and was able to enable the robots to succeed at the task more often. So the throughput increased, and surprisingly, the human performance also increased. So they were able, the humans were able to find more concentration pairs in that game of memory. So we can see that, being able to be judicious about when you request these interventions can give you better performance both with the human task and the robot task. And we gave the survey, and we found that the subjects found that our algorithm was less mentally demanding than something like ThriftyDAgger. We have to keep track of all these things at once, and also less frustrating than something like SafeDAgger, which was just constantly swapping between the task and the robots. So really quickly, some limitations in future work. So we saw that this algorithm can solicit many human actions, especially earlier on in training. So it might be better suited to kinds of tasks where a context switch is way more costly than an individual action. Say if you have to walk across a warehouse to control a robot or something. We also found that earlier states are biased to be riskier or thought of as riskier. That's both because the gradient has a hard time propagating all the way back, and also because intuitively you have a higher chance of failing the task if you're farther away from the goal. So some way of controlling for that bias would be good. And we're also interested in this interactive RL setting where you're not only learning from the human, but you're also learning from your own experience. Okay, that's it. Thank you for listening, and please check out our poster if you're interested.
Okay, great. Thank you, Ryan. And I think we have time for a quick question. Any questions coming up from online? Or Eric has one right here. Eric, we can always count on you. Go ahead.
What's the correlation that you see between the positive risk and positive novel?
Oh, whatever, it's fine. Okay. Wait, my mic is back on. Okay. So, yeah. So so often I would say novel states are often risky. Like almost always, like a novel state is going to be risky because you don't know what you're doing. The other case is less frequent. So there's not novel but risky. That is, I would say, less frequent. But it would be interesting to get those exact correlation numbers, as you said. Actually, I should probably run those. Yeah.
Well, it'll depend, obviously, on the task.
Right. Exactly.
Yeah. Okay, great. Other questions? If not, we're going to thank you, Ryan, for giving a great talk.